Hey guys, so we are going to do 4.2 today, which is all about graphing polynomial functions. And so this first little chunk is really just writing down the notes. And so I've screen shared those with you. And it says, if p of x is a polynomial function of degree n, then the graph of this function has at most n real zeros. And since zeros are x-intercepts, that means it has at most n x-intercepts. And it has at most n minus 1 turning points. Remember, turning points are relative mins and maxes. That's where on your graph you're shifting from increasing to decreasing, or you're shifting from decreasing to increasing. And so that's kind of important as we go through trying to graph these and determining what's going on in our graphs. So one of the strategies for graphing these polynomials is to first do the leading term test, that leading coefficient test that we learned in 4.1. We're going to do that, and then we're going to find all of our zeros, aka all the x-intercepts, aka all the solutions for this polynomial function, and we're going to make sure that we note the multiplicity for those different zeros, because as we've seen, what happens at those zeros is different depending on if we have an even or an odd multiplicity. Then we are going to find our y-intercept by plugging in 0 in place of our x for finding f of 0. And then notice on my notes, I kind of did a 3.5 shoved over there to the side, because it's always good to pick a point between each of your zeros to test to see where it's falling on your graph. And so I'd already kind of written out my notes before. I was like, oh, I should go back and add that, because it is always good to have a test point in between those zeros to figure out what's going on. After that, we should have a whole bunch of points that we are going to be able to plot, because we should have our zeros, we should have our y-intercept, we should have our test points, and then we can actually graph based on all of that information. Remember that leading coefficient test, or the leading term test, what it does is it tells us the end behavior. It doesn't tell us what happens in the middle, which is why we have all these other steps to help us figure out what's going on in the middle of our graph. So we're going to graph h of x equals negative 2x to the fourth plus 3x, that's to the third, not to the second, to the third. Okay, we're going to graph this. So first things first, we're going to use the leading term test to determine our end behavior of this graph. Well, our leading term is negative. And then our degree of this polynomial, we need to figure that out. The degree is the highest exponent. So in this case, we have a 4, which is even. So we have a negative even polynomial graph. And when it's negative, it means they're going to go down. And when it's even, they're both going down. So on either side, we're going to be going down. All right, now let's figure out some of our zeros. So that means we have to solve this. We set it equal to 0, and we have to figure out what our x's equal. So 0 equals a negative 2x to the fourth plus 3x to the third. And remember, the way that we need to approach this is by asking, okay, what do our terms have in common? Do they have anything that we can pull out that they share? Well, I know that we have an x to the third here, and I can take x to the third out of here because I have x to the fourth. So that would be 0 equals x to the third times a negative 2x plus 3. So I'm just kind of factoring out what they have in common. Now I can figure out what my zeros are, because I can set each of these factors equal to 0. Okay, so I have x to the third equals 0. Hopefully you're like, okay, well, x is going to be 0. And you'd be right. What you would do is you take the cube root of both sides, but you'd get x equals 0. Now, what is the multiplicity, though, of x equals 0? Remember, multiplicity is how many times are we getting x equals 0 as an answer? Well, you can look at the power, and that'll tell you your multiplicity. we have a power of 3. So this means we have x equals 0 with a multiplicity of 3. So what happens with a multiplicity of 3 or odd multiplicities? Do we bounce back or do we go through? And the answer is that we're going to go through. So I'm going to make a note here that we're going to go through. I'm going to set my other term equal to 0 so that we have negative 2x plus 3 equals 0. Subtract that 3 over. Divide both sides by negative 2. Negative divided by a negative equals a positive 3 halves. And then we have to determine the multiplicity of this one. Well, go up here. What is the exponent out here on this factor? And you might say, well, there isn't one. That's correct. So when there isn't one, we just understand it to be a 1. So this would have a multiplicity of 1. We're only getting this 0 one time. Multiplicity of 1, which means we're going to go through here. So we're going to go through at both of those zeros. When x is 0, we go through. When x is 3 halves, we go through. Try and circle those so they stand out a little bit more. Okay, so we've gotten all that information. That's great and wonderful. Now we need to figure out what our y-intercept is. Just slide us down a little bit. Try and keep all that on there if I can. To find our y-intercept, I'm going to take f of 0. Well, here's the nice thing. Look at our original problem. If I plug in 0 in place of my x's, what am I going to get? I'm going to get 0. So my y-intercept is 0, 0. Which maybe we could have deduced that simply by looking at the fact that we'd already gotten 0 as an x-intercept. And if that's an x-intercept, then obviously it's our y-intercept as well. All right, so now we need to, it says pick a point to test. So pick a point between our zeros. That's kind of our 3.5. So if we have a 0 at 0, and we have a 0 at 3 halves, then I'm going to pick a 0 at 1 and see what's going on there. So I'm going to find h of 1, which I guess this should say h of 1 since they gave it to us originally as an h of x function. Because 1 lies between 0 and 3 halves, so I'm going to test this point out and see what we're getting. So if I plug in 1, luckily 1 to the 4th is still 1, so that'll be negative 2. And then 1 to the 3rd is still 1, so that'll be 3. So I get the point 1, 1. Okay, so there's another point. So now I have all these different points that I can use to graph this polynomial. So I'm going to do a rough hand sketch. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. I know we don't need all those hash marks, but it feels a little imbalanced if I don't at least put them in there. So I know that I have a 0 at 0. So right here at 0, 0, I'm going to put a point. I know that I have a 0 at 3 halves, so I'm going to go over 1.5 and put a point. I know that my y-intercept is 0, 0. That's not very helpful because I already have it marked. But I also know I have this other point in here at 1, 1. So I can put that in there to kind of give me just an idea of what's going on. I know that at my zeros, based on their multiplicity, I'm going to go through and through. And I also know, based on my leading term test, that my ends go out and down like that. So do you see how we kind of just come up and we can connect in the middle to finish off this polynomial? And it looks very much like a quadratic. But they're going to get funkier because we're going to have a lot of other stuff going on. Okay? But this is the steps we're going to take every time we need to graph a polynomial function. We're going to use the leading term test. We're going to solve it and find our zeros. We're going to look at their multiplicities. Then we're going to find our y-intercept. And then we're going to test some points that lie in between all of our zeros to see exactly what's going on. I'll scroll up a little bit, like so you can see my little graph there. But I'm actually going to leave up these steps because we're going to use them again on the next example. And so that way you have them to reference as we're going through this next one, which is slightly more complicated of a polynomial function. All right, let me get my black. This time, we're going to graph f of x equals 2x to the third plus x squared minus 8x minus 4. If you happen to have my notes pulled up, this is just example B that we're going to work through. So you can see them there. Again, first things first, leading term test. I have a positive leading term, and the degree of my polynomial is 3, which is odd. So I have a positive odd going on. Positive odd means my graph is going to go down and up like this. All right, so now I know my end behavior. Next, I'm going to solve and figure out where my zeros are. Now, this particular polynomial has 4 different terms in it. We have an x to the third, an x, and a constant. Typically, what we're going to do then is we're going to factor by grouping. And remember, the whole point of factoring by grouping is that when you get your parentheses set up, you want the same thing inside of those parentheses. So let's see if we can do that. I have 2x to the third plus x squared minus 8x minus 4. So what I'm going to do is I'm going to look at these first 2 terms. And I'm going to say, okay, what does 2x to the third plus x squared have in common? Well, they both have an x squared in common. I can pull that out. Where I have an x squared times 2x plus 1. So I just pulled out what they shared and what they had in common. Then I do the same thing for my next 2 terms. I have a negative 8x minus 4. So what can I pull out of those that they have in common? Well, they both share a negative 4. If I pull that out, that'll leave me with a 2x plus 1. Notice that inside of my parentheses, we have the exact same term, and that's what we're wanting. If we factor by grouping and we don't get the same thing inside, then we're really not accomplishing much. And maybe over here, you didn't notice that you could take out a negative 4 to get started with, and you just pull out a positive 4. And if you do that, then you'll see that the signs are backwards, and then hopefully at that point, you'll realize you can pull out a negative as well. The reason why, though, we have to have the exact same thing inside of our parentheses is because now I'm looking at it and I have a binomial. I have something that only has 2 terms. I have my green term here and I have my blue term here. And so if I'm looking at just those 2 terms and I say, okay, what do they have in common? Since I made sure that what's inside the parentheses are the same, I can factor that out to where now I have the 2x plus 1 times the x squared minus 4. That's what I'm left with once I factor out that 2x plus 1. So now I can go about this in 2 different ways. I can set each of my terms equal to 0 and solve for my x, or I could go ahead and factor this one more time, recognizing that this is a difference of squares. And so either way is totally fine. Either way, you're going to get the exact same answer. In my notes, I go ahead and take this one more step further because I recognize that this is a difference of squares. And so I recognize that I'm going to have 2x plus 1. And then by factoring a difference of squares, I'm going to have an x minus 2 and an x plus 2. Now that everything is completely factored, I would set each of my terms equal to 0 to solve for my x's. This first one, the 2x plus 1, that would give me x equals negative 1/2. Because I would subtract my 1 over and then divide by 2. The next one would be x equals +2, because I would add the 2 over, and the last one would be x equals -2. So those are my 3 zeros that I'm going to have for this polynomial function. Remember, based on just the definition of our polynomial function, we can have at most n number of real zeros. That means the degree of your polynomial dictates how many zeros you can have. I could have 1, 2, 3, or 0 zeros for this, but I can never have 4 zeros because it's a third degree polynomial. So a third degree polynomial is capped out at 3 zeros, and I got 3 zeros. And then let's look at their multiplicities. This doesn't have a power of anything but 1, 1, 1. So all of these have a multiplicity of 1, meaning I'm going to go through every time I hit a 0. There's no bouncing back on this one. So I'm just going to make a note of going through those. Okay. Next, I need to find my y-intercept. And to find my y-intercept, I would find f of 0. And again, finding the y-intercept with a polynomial function is very easy because most of our terms go straight to 0. That would go to 0, 0, 0, leaving us with just a -4. So I would have 0, -4 as my y-intercept. So I have all these different points going on right now, which is really good. But we still want to pick a couple of test points. We want to pick a test point that lies between -2 and -1/2, and one that lies between -1/2 and +2. And then I picked another one, but I'm wondering why I picked it. Oh, I didn't. That was just my y-intercept. So here, if I'm going between -2 and -1/2, I'm going to pick x as -1. So I'm going to find f of -1. And when I do that, I'm plugging -1 into each of these spots. So I have 2 times -1 to the third plus -1 squared minus 8 times -1 minus 4. -1 to the third is -1, so it'll be -2. -1 squared is a +1, so it's +1. Negative gives me a positive. Then I have that -4 out there. Combine these all together. Let's see, I have -1, +7, +3. So I get the ordered pair of -1, +3. Okay. Now I'm going to pick a test point that lies between x is -1/2 and x is +2. Now we kind of already have a point that lies in between here because we have our y-intercept, but it's still always a good choice to pick another one. So I'm going to pick f as 1. And it's going to be almost exactly the same here, only we don't have our signs to play around with. So 1 doesn't change if we cube it, so it's just going to be 2 plus 1 minus 8 minus 4. So that's -12, -10, -9. 1, -9. So now we have all these different points and bits of information that'll help us to graph a relatively nice polynomial. I am going to slide us, I think, this way to do the, maybe not. I'll slide us this way. You're going to lose some of the information, but hopefully it's on your paper, and I'll try to graph it all right here so that you can see it. Based on my points, I have to go at least up to 3 and down to -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 5. Okay. So we found out that we had a 0 at -2. So I'm going to put that in. We had a 0 at -1/2. Put that in. We had a 0 at +2. I have my y-intercept at 0, -4. 1, 2, 3, 4. So that's down here. I also know that based on my leading term test, it was positive and odd. So at the ends, I'm going down on the left and I'm going up on the right. So it's all this stuff in between that I'm kind of playing around with. But I did find out that I had a multiplicity of 1 for every single one of my zeros. So that means I'm going through here, then I'm going through here, and then I'm going through here. So I kind of just make notes of that. At -1, I went all the way up to +3. And at +1, I went all the way down to -9. So see, by having these points that go in between our zeros, we kind of get a better picture of what our polynomial is looking like, because it's showing us just incredibly how high or how far down we're going. Whereas before, if we only had our zeros, we would just kind of bump them, you know, and it wouldn't show quite dramatically how far down we went over here. And so that's why we do these little test points in between our zeros, because it really does make a slightly different picture than if I just connected. Like if I didn't do a test point, I would just connect here, and then I would come back up and connect here, which still gives us a pretty good general picture of what's going on. But I would have all of this gone, and I would have all of this gone, and we wouldn't see quite dramatically how that stretches down there. So the test points are helpful. All right, let's do another one, and then we'll talk about one more theorem that can be helpful when it comes to talking about our polynomial functions. Let me slide you back down. Okay. Let's get rid of some of this. If you happen to have my notes pulled up, we're going to do example C. C is in cat. All right. Okay, so like I said, this one is example C from my notes. So the nice thing about this one is that while they give you the original like factored out polynomial, they also went ahead and factored it for you, so you aren't expected to factor this 4th degree polynomial. Sometimes they will do that for you, and sometimes they won't. I would say typically if it's going to have like 5 or 6 or 7 or 8 terms or however many like that, they're probably going to go ahead and factor it for you just to make your life a little bit simpler. If there's like 4 or less terms, I would say you're probably expected to go ahead and factor that. But this one they already factored for you, but we still need to look at the leading term test to determine our end behavior. So there is no term written right here in front of our highest ordered polynomial, the highest degree polynomial, or excuse me, term. And so we understand that that's just a 1, and there's no sign there, so that means we have a positive. And then we have this 4, which is even. So we have a positive even function. That means we are going to go up and up on our endpoints. So that's good to note at the very beginning. And then the nice thing here is that since they've already factored it for us, that's most of the work when it comes to finding our zeros. Because all we do is we set each of our terms equal to 0, and we look at the powers to determine their multiplicities. So when x plus 1 equals 0, that means x equals a -1 with a multiplicity of 1. That means we're going to go through there. When x minus 2 equals 0, we find that x is +2. And here we have a multiplicity, because there's a power of 2 here, of 2. That means we are going to bounce back there. So we'll go through here, we'll bounce here. And then when x minus 4 equals 0, that means x equals a +4. Multiplicity, again, in this case, there's nothing up there, so that's a 1, which means we're going to go through. Lots of good information there. Pretty minimal work, to be honest. So lots of good stuff right there. And there's our up here. So that's good. The next thing we're going to figure out is we're going to figure out our y-intercept. That's where we have f of 0. Again, the nice thing is we put 0 in here, it goes 0, 0, 0, 0. So really all we're looking at is that constant term down there on the end, which is -16. So we have 0, -16 as our y-intercept. Now, what we want to do after that is we want to pick some points that lie in between these zeros. So I need something that lies between -1 and 2. Again, we already did 0, so I'm going to test 1 because I like to pick the ones that are going to be algebraically easiest. So I'm going to find f of 1. When I plug that in, I have 1 to the 4th, which is 1. -7 times 1 to the 3rd, which is just -7. 12 times 1 to the 2nd, which is just 12. 4 times 1, which is 4, and -16. I do all of that so that I have -6, +6, +10, -6. So 1, -6. That's an extra ordered pair. So I know what's kind of going on in my polynomial. And then I'm going to pick a point between 2 and 4 to test as well. Bet you can guess which number I'm going to pick. I'm going to pick 3. Again, let's keep it as simple as possible. This one's going to be a little bit bigger though, because we have 3 to the 4th. 3 to the 4th is 81. -7 times 3/3, which is 27. And then we have 12 times 3 squared, which is 9. Plus 12, because 4 times 3 is 12, -16. Much larger numbers going on here, but that's okay. Because you know what? When we add them all together, we're actually going to get a small number. We have 81 minus 189 plus 108 minus 4. You type all that stuff into your calculator and you find out that it's actually just -4. So all of that work with all those ginormous numbers, and we really just are getting down to -4. So it's not as terrible as it might look. The 3, -4. Oops. Trying to stay consistent. 3, -4. All right. I've got my zeros, I've got my end behavior, I've got my extra points, I got my y-intercept. I am ready to graph this. Lots of good information. And my graph's gonna have to be a little bit big because my y-intercept goes all the way down to -16. So gotta make sure I get lots of little tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Keep going. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6. 1, 2, 3, 4, 5. I don't think I have to go up at all, but like I said, it makes me uncomfortable to leave it empty. All right, let's see what we're doing. We've got a 0 at -1. We've got a 0 at +2. We've got a 0 at +4. Those are all my zeros. I know that at -1, I'm going to go through. At +2, I'm going to bounce. So look at the way my graph is. I went up, so that means I'm going to be bouncing on this side. Oh, wait. I don't know why I did that. Correction. I wouldn't be going through that way anyways. Because what happened, I should have marked my end behavior first. Because what's my end behavior doing? My end behavior at the ends are going up and up. That means I'm coming at this -1 from this direction, meaning I'm going to go through here, and then I'm going to bounce here, and I'm going through here. So I kind of make little doodles there to let me know what's going on. Now I'm ready for my y-intercept, which is at 0, -16. That's all the way down here. I know that at 1, I'm at -6. 1, 2, 3, 4, 5, 6. So that's right here. And I know that at +3, I'm at -4. 1, 2, 3, 4. So I'm up here. So now I know that I need to go all the way down here to go through my y-intercept, come back up, hit this point. I'm going to bounce up that 0, come down and go, And there is like a super weird, wonky looking graph, but it is a pretty well little graph to help describe what this polynomial is doing. And so each of the parts of our polynomial play an important role. And so we don't want to leave any parts off when it comes time to graphing them. Now, I said that we were going to have a little bit more notes, and that's true. See, there's our big major honking graph right there in the notes. But we have a theorem that we're going to use that helps us to identify if there is a zero lying between some other points. And it's called our intermediate value theorem. And it says for any polynomial function p of x with real coefficients, that just means that they're real numbers, not imaginary. And if a does not equal b, then if p of a and p of b are on opposite signs, then there exists at least one real zero between those 2 points, thus an intermediate value theorem. And I think the wording of it is a little bit weird, but I can even show you on just this graph that we had here. So if I'm looking at this blue graph and all of its craziness, and I'm saying, okay, right here is A, like in terms of my X, right here is A. And so up here we have our F of A, right? And then I'm looking over here and I'm saying, okay, right here is B, and that means this is F of B. Okay, do we see how this is working? So A and B are not like at the same point. That's what I'm trying to show you. A happens over here, B happens over here. But look what happens with our F of A. Our F of A is positive. Our Y value here at this point is positive. It's up here. Our Y value down here, our F of B, is negative. And so if the signs are opposite like that, we can guarantee that there's at least one zero. There could be a whole bunch of zeros that lie between this point and this point. We don't know, but we can guarantee there's at least one because we have a positive Y and a negative B, and the only way to go from positive Y's to negative Y's is to go through the x-axis, which thus gives us an x-intercept. So that's what our intermediate value theorem says. So how do we use this? How is this helpful? Well, it's not really helpful in terms of graphing. It's just helpful in terms of our knowledge of what's going on in our polynomial function. So let me show you. You can see the example right here in the notes on the screen. It says use the intermediate value theorem to determine if there is a zero for the following function. And then it gives you an A value and a B value. So our function is f of x equals x to the third plus x squared minus 6x. Now here's the nice thing. We don't have to solve this. We don't have to graph this. We don't have to do anything. What we're going to do is we're going to look at a equals -4 and b equals -2. And we're going to use the intermediate value theorem to see if there is a zero between them. Now, we can only guarantee that there's a zero if when we factor, like when we plug these in and we solve, we have opposite signs. If they have the same sign, we can't guarantee anything because there could very well be a zero that lies between them, but we don't know that based on this theorem. We only know it if the signs are opposite. So what we have to do is we have to find f of a, which is f of -4. And then we're going to see if we get a positive or a negative solution. And then we're going to do the same thing with b. We're going to find f of b and see if we get a positive or a negative solution. So f of -4, that'll be -4 to the third, which is -64 plus -4 squared is a positive 16. -6 times -4 is a positive 24. -64 plus 40 equals a -24. Now, the number itself doesn't really matter. What matters is the sign. So we have a negative. So if when we find f of b, we get a positive answer, then we can at least say that there's one zero, at least one zero that lies between those 2 points. So this would be finding f of -2. -2 to the third is going to be -8. -2 squared is a positive 4. -2 times -6 is a positive 12. So we have -4 plus 12 is a positive 8. So since these have opposite signs, I can guarantee that there is at least one zero that lies between them. There could be 2 zeros, there could be 3 zeros, there could be, well, I guess we can't have 3. Well, yeah, we could have at most 3 because it's a third power. But it doesn't tell me how many, it just tells me that there is one. So I do know that there's at least one that lies between -4 and -2. Okay, then we do the exact same thing, but we're going to have 2 different points this time. We're going to have a new A and a new B. So this time, A equals -1 and B equals +3. So we're using the same equation. We're just using new A's and B's. So f of -1, -1 to the third is -1, -1 squared is a +1, and -6 times -1 is a +6, meaning I have a +6. Okay. So I need f of b to be negative in order to guarantee that there is a 0 between there. So f of 3 to the third power is 27. 3 squared is 9. Minus 6 times 3, which is 18. So this would be 36 minus 18, which is 18. Now, these have the same sign. So I cannot guarantee that there is a 0 between these. Now, if I graphed it, I might be able to show whether there is or there isn't. But solely based on the intermediate value theorem, I can't tell you that there is a 0 or there's not. And so I would say I cannot verify this at all. There could be, there might not be. So that's kind of the limited range of the intermediate value theorem, is it does give you some helpful information, but it's also limited in that if you have the same sign, then it's not going to give you a lot of information. But that is the end of 4.2.